Okay.
Good morning, everybody. How are you doing at Byron Center? Looks a little sparse over there.
Really?
Some people still traveling? Went by way of American Airlines, huh? Well, welcome back, everybody, and we have been plodding along, not real swiftly here, and I assume you've been keeping up, right?
Yeah.
This is the planned agenda for today, Monday, April 14. There's some homework problems in 10.2 you might want to go over. Some different ones in there. And we have to head for sections 9.1, 9.3. We kind of combine those together. So that's the plan for today. I assume you have all the materials, right? Okay, here are some answers to the even-numbered problems in 10.2. So even if you haven't had a chance to work all those yet, we'll give you a chance to write them down so you have something to shoot for.
I would say yeah.
Oh, thank you.
That's not normal.
I'll probably pull them in like 5 minutes while I get some cold.
How about 2 minutes? Okay?
Yeah.
Close at 7:25. It wasn't this hot over break, and it's going to be this hot now.
Please listen to me.
Sorry.
I thought about it, but then I sounded trash.
I told you.
How can I just not hear you? I gotta say something. I couldn't say anything. I was like, I'm not gonna do it. I just see it and I want to I gotta get
Oh, yeah. How?
Morning, Katie.
Leave these up for just a little bit here. We have a lot of late people this morning. I have to start locking the door so you can't get in after 7:15.
I got really late, and then I had 3 hours. Yeah. Oh, Saturday is 6 and 9. Wow.
Right now.
That was my grandmaster, I can't reply.
Liar.
No, if I was very late.
I did actually.
Okay, is there anything you want to go over in section 10.2? Problem like number 30? Okay. We've done this sort of problem in Cartesian, and I think a similar procedure might work. One thing we kind of like to do is get a picture of what's going on so we have an idea of how many answers we might get. So we're going to do a quick drawing of the curve and try to anticipate what might happen. So we'll get our calculator up here and see what that curve looks like. Okay, I have to get back in parametric mode. Okay, the first equation to generate that curve is 3y squared plus 1, 3t squared plus 1. And the second one is 2t cubed plus 1. And here's the standard window look. I don't know, I have a feeling there's more to it than that. So I'm going to expand my window a little bit. We'll go minus 2 pi all the way to 2 pi and see if we get more of a curve. Ah, that's more like it. Okay, now they're going to have a point out there at 4, 3. That would be kind of between the curves somewhere. Right up in here. And they want to know what tangent lines to the curve would look like. Well, we'll kind of redraw that on a piece of paper. And my guess, based upon what I've seen, is there's a possibility of 2 tangents. Because one comes down like this and the other one goes like that. And my point is in here somewhere. So it seems like eventually you could get a tangent line going up that way to the curve, and maybe another one going down this way to that curve. So the only purpose of doing that was anticipate how many answers should I get. And I would guess probably 2 tangents at this point. Okay, to begin this particular problem, we are going to pick a random point on the curve, let's say right there. We'll call it AB. This point, of course, is 4, 3. And I want to find the equation of that tangent line through 4, 3, and AB. Now, AB, of course, is a point of tangency on the curve. So it better satisfy the equation of the curve, which means that A has to equal what? A is the x-coordinate, so A better equal 3t squared plus 1. And the B better satisfy the equation 2t cubed plus 1. In other words, if I put A in place of x and B in place of y, I better get truth. Otherwise, that point's not on the curve. So this is one set of facts that I know. What else do I know? Well, when we solved this kind before, we knew that slope had something to do with finding an equation of a tangent line. And how did we find the equation of a tangent line as far as slope is concerned? Yes, we took a derivative. And we learned the other day that you can get this parametrically by taking the derivative of y with respect to t and dividing by the derivative of x with respect to t. Now for this particular curve, of course, x is 3t squared plus 1 and y is 2t cubed plus 1. So therefore, what's the derivative of y with respect to t? 6t squared, right. What about the derivative of x with respect to t? 6t. I think that reduces, doesn't it? What's 6t squared over 6t? All right, so the equation of a tangent line to that curve, no matter where it is, has to be t. Slope of the tangent line to the curve has to be t. What's another way to get slope of that tangent line that I drew in the picture? Algebraically, remember, change in y over change in x. So this represents slope, but b minus 3 over a minus 4 also equals slope. I can get slope 2 different ways. And maybe this is starting to look a little familiar, I don't know. But if these both represent slope, then they better equal each other. So I got t equals b minus 3 over a minus 4. But, you see up here in the circle? What can I replace b with? Yeah, it has to equal 2t cubed plus 1 because it's on the curve, and if it's on the curve, it's got to make the parametric equations true. What can I replace a with? Yeah, the 3t squared plus 1. So replacing b with the 2t cubed plus 1 and the a with 3t squared plus 1, I now have an equation with strictly t in it. So I think I should be able to solve that for t. So I now have t equals 2t cubed minus 2, all divided by 3t squared minus 3. Just simplifying a bit. Okay, if I get rid of the fractions, like multiply each side by 3t squared minus 3, I get 3t cubed minus 3t on the left equals 2t cubed minus 2 on the right. And combining like terms, that's a t cubed minus 3t plus 2 equals 0. And if I can solve that equation for t, that'll tell me the slope of my tangent line or tangent lines if there's more than one. But if there's more than one, I would get more than one value for t. And you say, but that's a cubic, that's not fair. Well, I felt that would be okay because this thing can probably solve it, right? Actually, you can almost solve it by looking at it. But we'll pretend we didn't notice that. So you can just go to the home page and go to algebra, solve this equation. T to the third power minus 3t plus 2 equals 0, comma, solve it for t. And the calculator says there's two real answers for that, namely 1 and minus 2. What does that mean? Well, what did t stand for? The slope. Remember, that's what it reduced down to? So using the calculator, minus 2 and 1 pop out very quickly. So back to the paper. We got t equals negative 2, and we got t equals 1. Now I go to my picture and say, is that reasonable? Could those be the slopes? Yeah, I would say this one going up this way could have a slope of 1, right? And the one going down that way could have a slope of minus 2. Sure seems to fit pretty good. All right, now to finish the problem. One equation of a tangent line is y equals mx plus b, where m equals 1. And what does it take to find b? Any point on the line. Do I have a point? Yep, 4, 3. So I put 3 here. And that's how we got b equal minus 1. So one equation would be x minus 1. And the other one we put minus 2 in. So that's my optional slope. Same point though. So if I put 3 here and 4 there, I end up with b equals 11. So the other one would be minus 2x plus 11. I thought it was kind of a nice problem. What'd you think? Stinks? Yeah, I had to do a little thinking and planning, but that doesn't bother you guys. you prefer when you have to think and plan a little bit. Otherwise it gets boring. So anyway, for what it's worth, that's number 30. Were there any others in there that you'd like to check more closely? Weren't quite sure just how to make it happen? Which one? 25? Okay. That's kind of a show problem. Show that this thing has two tangents at 0, 0, and then find their equations and sketch the curve. I think I'll sketch the curve first. It doesn't say you better do it in a certain order, right? Okay, let's see what the curve looks like. Okay, getting rid of some of the other ones. For problem 25, one curve is cosine t. We can do that. And the other parametric equation is sine t times cosine t. So there they are. It doesn't really say how to set the window, so I'll probably just leave it the way it was, and we can always adjust. I think I might want to adjust it. It's kind of tiny. Plus I'm drawing it several times. It's kind of an interesting one. So let's make it a little bit bigger as far as the screen is concerned. One corner of the box. And a second corner of the box. Oh, so I finally have the equation of what? The infinity sign. Wow, this is exciting. So that's where the infinity sign comes from. It actually has a graph. Yeah, parametrically it's kind of nice. It's x equals cosine t and y equals sine t times cosine t.
What's your window?
What's my window? I just zoomed a box on it, but I'll show you the window. I'm going from minus 6 pi to 6 pi, but I drew it twice, so I probably don't need that much t. My x minimum is about minus 1.35. The max is about 1.43. And the y min is about negative 1.37. And the y max is about 1.18. Okay? But I just put a box around it, and whatever it gave me, because I wanted to make it a little more apparent just what figure we got there. Okay. Now that I get over my fascination with the fact that the infinity sign has a equation. Wow. What's the question? Well, it says show that the curve has two tangents and find their equations. That's at the origin. Well, I can kind of see that because I guess one equation would be following the curve kind of along like that, wouldn't it? That would be one tangent. So that would probably have a negative slope. And the other tangent at the origin would be one that follows the curve this way. Probably has a positive slope. So I guess we've shown it. I guess that one's over. I think they wanted it to be done symbolically, because otherwise it'd be too much fun. Just draw the picture and put your ruler on it and say, there it is, next question. Well, there's one problem. It says find the equations. They're not on the calculator. I think we sort of showed it probably has two. Now we got to find them. Okay. Looking for the equations of the curve. Well, as is typical, my answers are going to look like this, right? And you know the routine from Calc 1. You had to do it over and over and over again. Find the equation of a tangent line. And the first thing we always went for was the slope. And we always got slope the same way. What was it? Took a derivative. Okay, my parametrics are x equals cosine t and y equals sine t cosine t. Okay, if I take the derivative with respect to x, which is the same as taking the derivative with respect to t and dividing by the derivative of x with respect to t, I should be able to get my slope. That's the standard way we've been doing slope for centuries. What's dy dt? Ooh, there's a big dot here. Did you see it? So it's the first times what? Derivative of the second, that's minus sine t, plus the second times the derivative of the first. Okay, what's that going to be over? Okay, let's simplify it a bit. I see a cosine squared t minus a sine squared t all over sine t. That's my derivative in terms of t. Cosine squared t minus sine squared t over sine t. Minus sine t, sorry. Of course, that could be rewritten as sine squared t minus cosine squared t all over sine t if you want to get rid of some negatives. Okay, what's the derivative therefore? To help me find the slope, okay? Where did I want to find slope? At 0, 0, right? The problem is, when I'm at the origin, what is the values of t that put me there, right? Well, how could I find that out? Just replace x with 0 and solve for t. Oh, then I get cosine of t equals 0. What's the value of t that does that? Pi over 2. And the next time it happens? 3 pi over 2. And so on, right? It keeps on doing that. Okay, now what you have to check at this point, and that's where the graph is significant.
Just a reminder, today is even way to go to your even
Does that take you through the origin twice? That's the question. Well, that's easy to check. I'll just set my t step in the window, or my t values, I should say. I'll just set the t values in the window to include these and see if I get a complete trip twice through the origin, one from one way, one the other. Okay, the first time, and here's where the calculator is really handy. It was much harder to do this without calculators in my day because you had to do everything by hand, but you go to the window and you just say, okay, I'm going to go from 0 to pi. Because that takes me through pi over 2, doesn't it? And I'm wondering if I'm going to get enough of the curve to generate one of the two tangents. Well, here we'll find out. See what I'm doing? So if I go from 0 to pi, that's as much of the curve as what I get. And won't that part, because pi over 2 puts me right at the origin, we just checked that out, but won't that give me this one? Okay, and then if I continue all the way to 2 pi, then it should continue and give me the rest of the curve that gives me the tangent going the other way. Now I'm only going from 0 to 2 pi now, and I did get just one trace over the curve. But along the way, where are you going to hit the origin? First time at pi over 2, and then on the way back at... So what's my point? My point is I have enough information now, just using those two angles, to get what I need. One tangent going one way, one the other. Okay, if, first of all, t equals pi over 2, and you remember the curve, then dy dx, that derivative, is going to give me sine squared of pi over 2 minus cosine squared pi over 2 divided by sine of pi over 2. And because we're working with pi over 2, it works out pretty nicely, because what's the sine of pi over 2? Yeah, it's 1. So you end up with 1 squared minus 0 squared over 1, which is... So the slope of one of the tangent lines is 1. Guess what the other one probably is? Probably negative 1. But we can check that by putting in 3 pi over 2. It'd be sine squared of 3 pi over 2 minus cosine squared of 3 pi over 2 divided by sine of pi over 2. Okay, sine of 3 pi over 2 used to be minus 1, but I got to square it. Cosine of 3 pi over 2 is 0, got to square it. And minus 1 on the bottom. What's the net result of that? Just like we predicted. Okay, are you pretty good now? I have to do y equals mx plus b at the origin. One time the slope is 1, and the other time the slope is minus 1. So I bet one of the answers is y equals x, and the other one is y equals minus x. Is that good? So that's the routine problem from Calc 1, only in parametric form. Find the equation of a tangent line somewhere at a point on the curve. Same technique, find the derivative to get slope, and then use algebra to finish off the equation. But we get to find the slope parametrically using our new derivative formula. Anything else we need to check? Section 10.2. Okay, I promised to come back to 10.2 again on Wednesday and just see if anything else came up. We can check 10 yet today, yeah. No problem. Okay, in problem number 10, we have x equals the cosine of t plus the cosine of 2t, and y in that same one is sine of t, and plus sine of 2t. And they say run your parameter from minus 1, oh, not inclusive though. And they said find an equation, no, that's not right, read the problem. This is the point of tangency, okay. So find the equation of the tangent line to that curve at minus 1, 1. Okay. I know that you know the routine you have to go through, you just want to check some of the details, so let's see if we agree with dy dx. First thing I have to do is take the derivative of y with respect to t. So I got a cosine t plus the cosine of twice t, and that was times 2. You did remember the 2, right? Chain rule? Okay, the derivative of x with respect to t is minus the sine of t, minus, sine of 2t, and that's times 2. But now I need to know what t value to plug in there. See, these are x's and y's. So I've got to find the t values that go with that point. So I said, let 1 equal sine of t plus sine of 2t. You can use either one, but I thought I'd use the second one because then I can keep it more positive. You could put minus 1 in the first one, it won't make any difference. Okay, I got to solve that for t. Well, that's where the fun comes in. In trig class, when this happened, we said change sine of 2t using a formula, namely 2 sine t cosine t. There's a trig formula for sine of 2t. You say, well, how does that help? Well, now I got to try to solve that. But I have a 1 on that side, right? Too bad I don't have a 0, then I could solve it. So how do I solve that equal to 1? Well, factoring really isn't going to help because factoring only works if you have one side equal to 0. So what can we do? Got to find the value of t that makes that true. Well, I thought it might be fair because if you weren't sure exactly how to do that, you have this thing, right? I think the book says you can kind of figure it out pretty easily. Well, let's see what the calculator does first, and then I'll show you why the book thought even if you didn't have a calculator, you should still be able to get it because the equation has some special things in it. But we're going to go to F2 and say solve 1 equals, and the problem is when and we'll help the calculator along a little and do the substitution for it. But when the calculator solves trig equations, it writes the answers weirdly. And you have to know how to interpret it. I'll show you what I mean. It can't do it. Solve 1 equals sine t plus 2 sine t cosine t for t, and it says can do it. That's amazing. This is a simple equation to stump the calculator. Well, maybe it likes it better the way it was originally. I don't know. I was just trying to help it. Let's, instead of the 2 sine t cosine t, let's put in sine of 2t and see if it can do better. Yeah, it did a great job. It switched the terms around and says, it's kind of laughing at us, isn't it? It says, oh, you want to solve this? Good luck. Oh, I didn't think it was that bad. I didn't try to solve it on the calculator because you can kind of see the answer by just looking at it, but I thought it was easy enough. You got to get 1, right? And I changed it to this because here you have a sine and a cosine. So I said if I could get this to drop out, well, the only way I could get that to drop out is to make one of these 0. And then I said to myself, sine of what is 1? Sine of what angle is 1?
0.
No, sine of 0 is 0. Sine of pi over 2, that's right, is 1. What's the cosine of pi over 2? So if I replace t with pi over 2, isn't it pretty obviously a solution? I think that's what the author was thinking. I thought for sure, though, the calculator would get that. I mean, isn't it pretty obvious now that you see it? If I replace t with pi over 2, doesn't that make it true? Yeah, one answer is t equals pi over 2. Of course, one answer is good enough. Well, what does it mean that there's more than one answer? Well, if you extend your t value, doesn't the cursor just keep traveling over the curve many, many times and goes through the same point? But t equal 2, pi over 2 should produce that, right? Does it? I think so. Let's see if it makes x true. You see, I've got to get this point out of it, right? So I say when you have that point, t is pi over 2. That's what I'm saying. Well, you can, we know it works in the second one. Does it work in the first one? What's the cosine of pi over 2? 0. What's the cosine of twice pi over 2? Yeah, it's cosine of pi, which is -1. See, it works. So the author thought, yeah, it's not a standard type trig equation to solve, but it's one where the answer kind of flies off the page. I see you're not impressed. But anyway, now that I know that t has to be pi over 2, I can plug pi over 2 in here to get slope. So we'll go maybe one step further, and then if you're good, we'll stop. If not, we'll keep going. So we're going to take the circled equation, and we're going to find dy dx precisely when t is pi over 2. That means I have to take the cosine of pi over 2. I have to add the cosine of pi times 2, because twice t would be pi. And then I have to divide by minus the sine of pi over 2 minus the sine of pi multiplied by 2. The top becomes 0 minus 1 times 2. The bottom becomes -1 minus 0 times 2. What's the net result of that? So it's going to be a y equals 2x plus b. We're almost there now. I mean, the point of tangency is -1, 1, right? So 1 equals 2 times -1 plus b. That makes b about 3. I bet the answer is y equals 2x plus 3. I don't know. We'll never know because it's an even problem, so we got to accept whatever I get. Hate it when that happens, don't you? I have much more faith in Bob. I used to be Bob, so fear not. Does that answer your question? Did you get hung up trying to solve that little equation right where I did? Yeah, I debated on that one. And then I thought, it's good that they see what happens once in a while. Calculator gets stumped. I didn't know that because I hadn't tried it on the calculator before. And we don't have a standard trig technique to do it. But sometimes I've learned you just step back and say, is there an obvious answer here maybe? Usually we're too intent on trying to find a big symbolic fancy answer, solution. And sometimes you just sit back and say, duh, I can see what that is. Okay, sorry. I didn't mean to make you feel bad or anything. Any other questions from 10.2 at this point? Okay, like I said, I promised to come back on Wednesday, see if something else came up. Don't forget to try problems like 32 and 33. They're different. The hardest problems to do are areas. Got to really focus when you do those or you get off. with your integrals. Okay, the length problems and the distance problems, 37 and on, they're pretty straightforward because you have the formula just to plug into. You don't even have to hardly think. The one thing is we pointed out that distance and length are not always the same because you can travel a curve more than once. So length just says this is how far it is. Distance is, well, how many times did you go around that track? So you got to watch the two. They're not always the same. Otherwise, it's no big deal. But when you graph it with the leading cursor on, you can see how many times it travels over the curve. So that's not an issue anymore. Okay, we are going to head into a little change of pace. It's chapter 9. It's solving differential equations. We are in fairly good shape because we have to do differential equations, and then we have 10.3 and 10.4 to do. Yes, sir.
Example 5.
Oh, I said, remind me, we didn't get to do example 5, did we? Okay, let's go do example 5. That's left over on the last handout, 10.2. Okay, I'll get mine out. Okay, I think I did have a wrong page number on that example. Because I think I said 537, but the example is actually on 637. Yeah, 637, number 52, it's trying to make a point out of the difference between distance and arc length. So left over from 10.2 handout. It's the example page 637, not 537, and it's problem 52. Okay, in problem 52, they say here's a couple of parametric equations. X equals cosine squared t, y equals cosine t, and they want to go 0 less than or equal to t less than or equal to 4 pi. Okay, there are two questions. A, got to find the distance traveled. And B, you have to find length of the curve and compare. Okay, the first thing I do is find out if I go from 0 to 4 pi, how many times am I traveling this curve? And then I got to find what do I have to cut it down to so I travel it just once, because that would be the length. Okay? And again, this thing is quite helpful with all the features that it has. So going and getting this new curve in, cosine squared t, we have to type in as parenthesis cosine of t and then squared later, otherwise the calculator doesn't like it. And the second one is just plain cosine of t. And we'll start by setting our window from 0 to 4 pi. Okay, I don't know if the rest of it is good or not, but we'll soon find out. We're going to go from 0 to 4 pi. Here comes the graph. Ah, it's a pretty good window. I can see that the distance traveled is not going to be the same as the arc length. Right? Because with that leading cursor on, you can see it traverse the curve like how many times? Did you count them? Oh, you say it went too fast. Oh, okay.
Went twice.
Let's slow down the curve a little bit. And we can do that by changing the t-step. 0.07 will slow it down a little bit. All right, you got to count now. How many times did you traverse the curve? Here it comes. we slowed it down for a Monday morning. There's one time it went over it, okay? That would be 2 times it traveled over. Here's the 3rd time. And here's the 4th time. I think it's going to quit. Yes, so distance is what? 4 times the arc length? Now if 0 to 4 pi got me doing this curve 4 times, then what would do it 1 time? Okay, let's change that a minute. And we should see just 1 time. Okay, so we got everything we need off the calculator. Now it's just a matter of doing it. If I want to find distance traveled, I've got to take the integral from 0 to 4 pi of the square root of dy over dt squared plus dx over dt squared dt. And if I want to find the length of the curve, I just go from 0 to pi, or go to the last answer and divide by 4, or do the second answer first and multiply by 4. We're not going to be fussy about that. Okay, so finding the length of the curve, since that one's on the bottom, it's from 0 to pi. And then we got to find dy dt. Well, what are x and y? Well, x was the cosine squared of t, and y was the plane cosine of t. Okay, what's the derivative of y with respect to t? Okay, don't forget to square it. What's the derivative of x with respect to t? 2 cosine t minus sine t. And don't forget to square that thing, and then dt on the end. So basically, if I just want to find the length of the curve, I go from 0 to pi. And what I have under the radical is sine squared t plus 4 cosine squared t sine squared t. And I think that one is doable by hand, because you could factor out a sine squared, but we'll just finish it on the calculator and see what that turns out to be, and then we multiply by 4 to get the exact answer. So going to F3 number 2, I have to integrate the square root of sine of t squared. This is going to be a parenthesis nightmare. And then I have to go 4 times the cosine of t squared and multiply that by the sine of t squared. And then I need a parenthesis in the radical, and then I need a comma t, and then I need a 0, and then a pi. And if this works on the first try, I'll be amazed. But anyway, oh, busy, that's a good sign. There it is. The answer exactly is the natural log of 4 square root of 5 plus 9 over 4 plus the square root of 5. And of course, your boss would probably come to you and say, that's nice, but what is that? So you'd go diamond enter. And what's my calculator doing? It's probably converting that function to a series. And then it's going to add up a bunch of terms of the series. Why is it taking so long? Because that's what it's doing. You know how long that takes, right? And the answer is about 2.9579. So that would be the length of the curve. Then what would be the distance traveled? Just multiply by 4. So the top one would become natural log of 4 squared root of 5 plus 9 plus 4 squared root of 5. And the bottom one would be about 11.8315, I guess. If you multiply by 4, I think you get about 11.8315, give or take a point. Okay, that's the end of the last one, and the whole point of that problem was, if you are asked a question about distance and arc length, be careful. They're not the same. Make sure you define which one you need. Okay, that officially ends 10.2 then. Now, do the people here have the handout for 9? Oh, so if you're lucky, I didn't bring it along and we have to quit. Well, you are unlucky because I just about didn't. Okay, this is a little change of pace. I hope you enjoyed our time with parametrics so far. They're kind of unique, a little different. The only thing that can be kind of painful is integration, finding areas. Other than that, it's pretty much standard fare. I think it's kind of a nice thing to end the semester with somewhat, because you get to review a lot of Calc 1 and Calc 2 just before you go into Calc 3. Because finding equations of tangent lines was a big thing in Calc 1. Finding areas was a big thing in Calc 2. You have a mixture of integration and differentiation in a new setting. Okay, what is this next one? Well, it's solving differential equations. There is a course after Calc 3 called Diffie-Q. That is short for solving differential equations. You say, well, why are we doing this? Well, we want to take you to the threshold of what's coming. Well, what we're about to do with differential equations could be equivalent to this. You've taken algebra, right? Okay, when you started first year algebra, what kind of equations were you taught to solve? Linear. Right? And there was a systematic way to solve a linear equation. Remember, get rid of parentheses, combine like terms. You could almost do that in your sleep. Well, way back when you first entered algebra class, that was really hard. I mean, if I teach an Algebra 1 class, and we say we're going to solve linear equations, and somebody finally masters that, they think they're really mathematicians. You laugh, right? Say, you haven't seen anything. You don't know what lies ahead. You think you're a pretty good mathematician because you can solve a linear equation. Wait till you hit quadratics. There isn't one way to do those. There's like 4 ways to do it. And you got to decide which one to pick. And then once you've mastered quadratics, we go to cubics and fourth powers and logs and exponential, and you wish you had never opened the can of worms. But then it's too late. You're no longer innocent. You got to keep plowing on. Okay, you say, what's your point? My point is simply this. What we are about to do with differential equations is equivalent to solving a linear equation in algebra. That's how much of the surface you've scratched. That's why I gave you the analogy. You say, well, if it's like doing linear equations, I've got it made. Well, you're going to find that solving first order separable differential equations is more like solving log equations and stuff like that in algebra as far as the level of sophistication. Okay, that's my little introduction. Now for some of the details. That was just scary. So there's a whole course called DiffEq, because this only scratches the surface. It's like algebra class limited to solving linear equations and then think you've got it all. You don't. Okay, what is a differential equation is where we begin. What is a differential equation? How is it different than an algebraic equation? Well, when you solved equations in algebra, your answers were real or imaginary numbers, right? Answers were numbers. When you solve a differential equation, the answers are functions. Functions are solutions. So a differential equation is one which contains an unknown number, an unknown function, along with maybe some of its derivatives. So you say, well, what do they look like? Well, they're easy to make up, assuming that, y is equal to some f of x or something. An example of a differential equation would be x times y plus 3 times dy over dx minus x equals 3. Now that same one could be written as x times f of x plus 3 times f prime of x minus x equals 3. Now when you try to solve an equation like that, what you're trying to do is find a function you could put in there that makes it true. Maybe a function like sine of x. Maybe a function like e to the x. You're looking for some kind of a function that makes it true rather than a number. Here's another one. Y times the sine of x minus y prime minus 2y double prime equals e to the x. Looking for a function that makes that true. Something I can replace y with. Now what I want to be clear is we're not trying to replace x with anything. Y stands for the function, okay? So we're trying to find a function I could put in place of y, so that if I simplified all this, I'd get truth. All right, so what is the solution to a differential equation? It's any function which, along with its derivatives, makes the equation true. Okay, you can see a real parallel with what we're doing with algebra class, because when you first entered the world of algebra, what kind of stuff did we have you do first? We had some equations in front of you and we said, I think the answer to this one is 4. Verify that it is. And then what did you do? I mean, that was really hard. We give you an equation and say, we think the answer is 4. Can you verify it? And you actually had to plug 4 in for each of the x's and show that it worked. So the beginning was not find your own solutions. We said, here's a solution, you check it out. Well, guess where we start here? Solve these differential equations? No. Here's an equation. Somebody else solved it. Can you plug it in and see if they really did it right? So you should feel insulted. Okay, here it is. Example, page 571, number 2. Here's the differential equation. It's the derivative of y plus the tangent of x times y. We can put that in parentheses if you like to make it a little easier to read. Has to equal cosine squared x. And then they add something over here. They say whatever you pick for y evaluated at 0 has to give minus 1. So there's another little wrinkle. It's got to satisfy that condition, your y value. So whatever you pick for y has to be a function which evaluated at 0 gives minus 1. Okay, they said somebody who's traveled this road before solved this equation. And they said the solution is the function y equals sine of x times cosine of x minus cosine x. They claim that's the solution. Our job, verify. Verify that that solution is really correct. Well, how do you verify that something's really a solution? You plug it in and see if it works. The problem is, my equation doesn't just have y in it, it has, so I need something to put in there too. So the first thing I did is went for y prime. What's the derivative of sine x? Oh, it's a product rule. Well, that's okay. It's cosine x times cosine x plus sine x, and what's the derivative of cosine? There, now we use the product rule. And then I have to go minus the derivative of cosine again, which would be minus negative sine x. There, I did the product rule backwards from what I normally do. I went second times derivative of first plus first times derivative of second. A lot of you, half of you do it that way anyway. So I thought I'd let you know what it feels like. Okay, this would be cosine squared x minus sine squared x plus sine x. Does that look okay? For the derivative, cosine squared x minus sine squared x plus sine x. Okay, now let's plug them in. So we're going all the way back to here. And in place of y prime, we put cosine squared x minus sine squared x plus sine x. Okay, then I have a tangent of x, and that has to be times y. But y is supposedly sine x cosine x minus cosine x. And when that's all done, that's supposed to equal cosine squared, right? But I put a question mark on there because maybe it is, maybe it doesn't. That's what I have to show. Okay, working on the left-hand side, we can do the following. We have a cosine squared x, we have a minus sine squared x, we have a sine x, and you can't do much with those, but tangent could be replaced with what? Yeah, sine x over cosine x. And then we can multiply by sine x, cosine x minus cosine x. Okay, it's not getting any better. Sure doesn't seem to be a right answer to me. But I started distributing this. What's sine over cosine times sine times cosine? Yeah, it's sine squared. Okay, now we got to do that one. What's sine over cosine times minus cosine? Okay. Oh, look at this, just like magic. These cancel, and you're left with what? So what have we just done? We have shown that their solution actually does work. We plugged it in, and what happened? The left-hand side turned into the right-hand side. Okay, there's one more thing to do. They said your solution has to make this true too. So you got to verify that. So we still have to show y of 0 does indeed give minus 1. Well, what is y of 0? Let's going back to their choice for y here near the top of the screen and putting in 0 and see if it really works. So y of 0 is sine of 0, cosine of 0, minus cosine of 0. What's the sine of 0?
0.
Cosine of 0.
0. 1.
What's 0 times 1 minus 1? So what does y of 0 equal? So is it the solution everything they wanted it to be? Absolutely. So that's one type of problem. Not a real big deal. They give the answer. You verify they did it right. Okay, number 2. Why are differential equations necessary and important for certain situations? Well, in many applications of calculus, it's the rate of change. The rate of change is a problem that's known. You know a rate of change, but the function which has that rate of change, the one that satisfies the model of the problem situation, is not known. Whenever you know a rate of change, but you don't know what the function was that gives that rate of change, then the model becomes a differential equation in which the unknown function is the solution. And you say, well, I'd like to see one of those. I can't imagine that happening. Well, we just happen to have an example right here. It's on the back top of the next page. Can you picture this? I have a tank with a salt brine solution in it. And the tank holds 1,000 liters of salt brine. Okay, it starts out with 15 kilograms of salt dissolved in that 1,000 liters of water. Okay, so they must have dumped it in and stirred it up good. All right, well, it turns out that that solution is too strong. What do they use a salt solution like that for? Curing bacon, hams, stuff like that. But there's a certain percentage solution that you want to use. Evidently this one was too strong. So how are they going to make this solution less strong, less intense? Well, they're going to start pouring water into it, right? Just plain water. But as they pour it in, they have to let it out too, because they want the 1,000 liters. So pure water is entering at the rate of 10 liters every minute. Okay, the solution is kept thoroughly mixed, so you can picture this. It's got a mixer on it, and as the pure water runs in, it keeps mixing. And they let the water, or the solution, drain out of the tank at the same rate. Can you see this would make the solution less intense, less strong? Okay, now I have to find a model to represent the amount of salt in the tank after T minutes. Well, what do I know about this problem? I know the rate at which water and brine are entering, leaving the tank. I know a rate of change. But see, I need a model to represent how much salt is in the tank after T minutes, so I know when to shut off the water and say this is the right mixture. And if I had a model that, you see, maybe it'd be perfect when the amount of salt in it was 12. But see, it's all mixed through each other. So I want to know exactly when to cut off the water and shut the valve that's draining it. And I want to do it precisely maybe when there's 12 in there. How am I going to know how much salt is left in the tank? It's all mixed through and some's draining out. Okay, just like in a typical word problem in algebra, we're going to let something, I'm going to use y equal the amount of salt in the tank after T minutes. See, that way all the person that's doing the job has to do is set his watch, right, and let it run for 5 minutes, 7.5 minutes or whatever, and shut it off. And he automatically knows he has the right amount of salt in there, which makes the right mixture so he can use it. But that person doesn't know when to shut it off unless you can provide him with a function that gives the amount of salt as a function of T. Okay. Now the question is, how do I come up with that function y? So, we are not sure what the function y equals f of t is, but we do have information to get y prime or f prime of t. So we're not sure what the function is, but we do have enough information to figure out what the derivative is, because the derivative measures rate of change. Okay, what we are going to do is try to come up with the derivative function, and then if we can solve a differential equation, we can go backwards and find what the original was. Okay. There's something that's probably kind of important in this problem, and that is the concentration of salt. Concentration of salt is the next thing we focus on, concentration. That means if you could filter all the water out and just leave the salt behind, how much salt would be there? Okay, first of all, at the beginning, that's before we started adding water. What's the concentration? Well, how much salt was in there? So the concentration would be 15 in 1,000. That would be maybe sort of like the percentage of salt that's in there, maybe. But we call it the concentration is 15. And what kind of units would that be? Well, kilograms per liter, right? That's at the beginning. All right. So what would it be at time t? Well, how much salt is in the tank at time t? I know we don't know the exact number, but this is like algebra. We called it by a letter. Isn't y the amount of salt at time t? So what's the concentration at time t?
15 minus 6.
Y divided by 1,000, because the amount of fluid in the tank never changed, did it? We drained and added the same amount. Would that be the concentration at time t? Because there was y kilograms of salt when there were 1,000 liters. Okay, so if that's the concentration at time t, isn't that the amount of salt that's leaving the tank as it drains out the spigot? Because that's the concentration in there. So what is y prime or f prime of t, if you like? Well, that's the rate at which the salt is leaving. Well, rate is the concentration it's the concentration times the rate at which the general fluid is leaving the tank. How fast is the fluid leaving the tank? 10 liters per minute, and we write that as minus 10 because it's exiting, right, the salt. That'd be liters per minute. That's an L. And if we multiply that out, what do you get? Y over 1,000 times negative 10 would be negative y over 100. Now I kept track of my units so you could see what happens. See the liters cancel, and it'd be kilograms per minute. So that's the value of y prime, or the derivative of the function I really want. So as I said, there was enough information to find the rate at which the salt was leaving the tank. So minus y divided by 100 is the rate at which salt is leaving the tank. Now if I had a way to take that equation and get y from it, then I'd have an equation for the amount of salt that was actually in the tank. We'll solve for y later, because we got to learn the technique. This was just showing you a typical problem where a differential equation is natural. Okay? And what is my differential equation? dy over dx is equal to minus y over 100. So I have an unknown function y, which I'm looking for, and on this side I have the derivative. Now I need to figure out how can I solve that for y. Okay, here is the technique. So we'll be coming back to that problem and finishing it later, once we learn how to solve it. Okay, solving differential equations using separation of variables. Note, there is no single systematic technique for solving all differential equations. Well, that shouldn't surprise you too much. Is there one single method that solves every algebraic equation you could ever get? Is there one method that works for all linear? Yeah. Is there one method that works for all the rest? No. All right? So there is no one technique that solves everything. So we are going to limit our work in this section to solving what are called first order. What does that mean? That means there won't be any derivative bigger than first derivative. Second order means you could have second derivatives in it. Third order might mean you could have third derivatives in there. So it's called first order separable differential equations. First order separable. Well, what does a first order separable look like? Well, it's one that can either be written in the form dy over dx equals some f of x divided by g of y, or it's one that can be written as dy over dx equals f of x times g of x. I mean g of y. F of x times g of y here. So first order separable means you can either make it fit this form or make it fit that form, one of the two. Note that the word separable comes from the fact that the right side of the equation can be separated into either a product or a quotient of a function of x and a function of y. That's what first order separable means. So there's no derivative bigger than first derivative. In the right hand side there's a function of x there and a function of y, and they're either multiplied or divided. Okay, what's the technique if they happen to be unique and look like that? Okay, we first write the equation in the form dy over dx is equal to f of x divided by g of y. What if the equation is a product? Then fix it up so it looks like this. You want it to be a quotient, and you notice you want the x function on top and the y function on the bottom, okay? All right, rewrite it in the form. You do a cross product basically, and you say g of y dy equals f of x dx. So once you get it in that form, you kind of do a cross product. And once you get it looking like that, you integrate. You integrate both sides of the equation. In other words, you change it to the integral of g of y dy has to equal the integral of f of x dx. Now that shouldn't be too surprising to you, because when you have a derivative and you want to get to the original function, what do? You take an antiderivative. But isn't an antiderivative and doing an integral the same thing? Okay, then we just say after you get it like that, solve for y when you're done if possible. Okay, just happen to have a couple of examples to look at to get us started. And the first one is kind of a dream come true. Why? You don't even have to doctor it up. It's ready. You notice on the left I have dy over dx, and on the right what do I have? A function strictly with x in it on top and a function with y in it on the bottom. So what do you do first? Cross product. 3y squared dy equals x plus sine of x dx. Okay, next move. Integrate both sides. Okay, what's the antiderivative of 3y squared? We get to practice our integrals. That's what we started the semester with. You mean I might have to use substitution sometimes? You think I might have to use parts occasionally? You never know. There's method to the madness of the sequence in which we're doing things. Anyway, you don't need anything special for that one. We're not going to make you do anything fancy on the first one. Antiderivative of 3y squared is rigged.
Next third.
Just plain y to the cube plus maybe some constant. Remember that? Antiderivative of 3y squared is y cubed. Okay, what about the other side? Antiderivative of x. Okay. Antiderivative of sine minus cosine, plus maybe some constant. Okay, what's left to do? Just solve for y. Okay, first of all, y cubed could be written as x squared over 2 minus cosine of x plus some constant c, right? Because I could subtract c1 from c2, it's just going to be another constant. So what would y equal? The cube root of the quantity x squared over 2 minus cosine of x plus c. That is the original equation that should solve the differential equation at the top of the screen. So if you replaced y with this, and you replace the other side with the derivative of this, then you ought to get truth. Feel free to check it if you want to. So what do you think? Pretty easy, right? Well, let's try another one then. Maybe we have to do a little more work on this one. How do I know that's a differential equation? Well, it has a y in it along with its derivative. But this one I think we have to do a little more work up front. The other one was ready to just do it. What should I do to this? Change y prime into dy over dx so I can do my cross multiply. And what about the other one? You want it as a quotient so you can do your cross multiply, but be careful. You always want which function on top? The x, so when you cross multiply it goes with the dx. So how do I get y on the bottom so I cross multiply it with dy?
We lost the high school.
Oh, good, then we can really make time. Welcome back.
Hello.
We're here. Okay, so step one is make it look like the last one because that really worked well. And you see how y prime became dy over dx and xy became x over y to the minus 1. How do you know which one's on top, which one's on the bottom? Remember, you're going to cross product. You want your y's to match and your x's to match. All right, when we do our cross product, what do we get on the left? Y to the minus 1 dy. What do you get on the right? X dx. Okay, what do you do to both sides next? I'm going to change this to 1 over y to make it look more familiar. What's the antiderivative of 1 over y? Don't forget, this is important. It's natural log absolute y plus maybe some constant. And the other side? X squared over 2 plus maybe some constant. Now I have to solve for y. I have natural log of absolute y equals x squared over 2 plus c. Combine the c1 and c2. Okay, when we do one like this, there's a certain way they want the answer to be written, and that's why I always grab one. So, moving up here to solve for y. When you have a log equation, how do you get, in this case, absolute y equals what? Do you remember how to do that? Yeah, it's e to the x squared over 2 plus c power. That whole thing is the exponent. Okay. Now, the answer is going to look a little weird until you see a little bit how they're thinking. And they do expect you to do this. You take the right-hand side and you split it into 2 factors. Like that. Because when you multiply, you add exponents, right? Now, why do they do that? Well, e is a constant, isn't it? C is a constant. So they then say, well, this is just, this part I'm circling is just a constant. So they put a k in there. And unless you've seen this happen, you wonder, what in the world are they doing? But once you see it broken down, it sort of makes sense. E to the c becomes the new constant. I called it k. So what's y then? Well, I don't know. If absolute value of y was equal to 3, then what's y? Remember this? Plus or minus 3, isn't it? They both work. So the final answer is plus or minus k e to the x squared over 2. That's it. That's the way they're going to write the answer. Okay, we are going to stop at this point because I really do want you to go back to 10.2 and finish up what you didn't have a chance to do. It's kind of an important section. So if there's anything in 10.2 you haven't had a chance to do, make sure you do that by next time. And then just to practice a little bit of differential, you know, to get your feet wet. In that section called 9.1, there's not a lot of problems assigned there because that's basically, they give you the answer and you have to show that it actually works. So the only ones in 9-1 are 1, 3, 5, 7, and 9. That's all I gave you there. So focus on finishing 10.2. Try the problems in 9.1. And see if you can do the first differential equation in 9.3. Where you actually have to solve it. So, back to 10.2, do whatever you haven't done. Do 9.1. In 9.3, at least try one of them. See if you're okay on your own, okay? Try 2 if you feel really diligent. Any questions? Okay, we shouldn't have to push it too hard these last 2 weeks because after 9.1, 9.3, we have to do 10.3 and 10.4. And we've got this week and next week to do it. What you have to be thinking about is, do you want a 4th test next week? Well, think about it. Just think about whether it would be an advantage. Think about what it would cover. You know, parametrics and differential equations and polar. It's going to be on the final for sure, but I don't know if you want to squeak another test in. We probably could if you want to. You do have the yellow project too, though, to work on. I understand that. Maybe that's enough hay on your fork. I don't know. But next week especially, or maybe the end of this week, we're going to give you some class time to work on that as well, the project. So make sure you start looking at that. So if you have questions, you bring them to class and we'll talk about them as a group. Okay, that's it. See you Wednesday, same time, same place. Have a good day.